Hey everyone, welcome back to Let's Talk About Data. I'm Sonu Singh, and today we're diving into a super exciting hands-on project, building an autonomous web scraper that collects live data and helps you analyze real-time trends. We'll cover how to collect data from websites programmatically, web scraping, how to handle different data formats you might encounter, setting up your system to run this collection automatically, applying time series analysis techniques to understand patterns, using forecasting models to predict the future, and finally, putting it all together into an autonomous pipeline. We'll be primarily using Python, leveraging powerful libraries like requests, BeautifulSoup, pandas, and concepts from machine learning frameworks like TensorFlow, Keras, or PyTorch when we get to forecasting. Many of the core concepts, however, also apply to R. Our journey begins with collecting data from the web. While many websites offer structured data through APIs, giving you data in nice formats like JSON or XML, sometimes the data you need is only available on a standard web page. Extracting data from a complete web page and storing it in a structured format is called web scraping. Before you scrape any website, you must always check its terms of service and robots.txt file. Scraping without permission can be illegal or unethical. For our demonstration today, we'll use simple examples or publicly available static text files to illustrate the techniques, but understand that applying this to live websites requires caution and permission. Websites are built using HTML. It's a markup language that structures content using tags. For example, P for paragraphs, H1 for headings, A for links, table for tables, Li for list items. We need tools to read this HTML and navigate its structure. In Python, two excellent libraries for this are requests for downloading the page content and BeautifulSoup for parsing the HTML. Let's start by downloading a simple page. We'll use a static text file available online. The request.getURL command sends a request to the URL. Response.raise_for_status is a good practice to ensure the download was successful. For example, got a 200 OK status code. Now that we have the HTML content, or text content in this case, but BeautifulSoup handles both, we use BeautifulSoup to parse it. BeautifulSoup turns the HTML into a searchable tree structure. We can then use methods like find to get the first matching tag or find_all to get all matching tags based on their name, like P, Li, or attributes, like class, ID. This allows us to pinpoint and extract the exact data points we need from the page. Remember, each website structure is unique, so you need to inspect the HTML source using your browser's developer tools to find the right tags, classes, or IDs. What about data served via APIs? Often this data is in JSON format. Requests handles this beautifully. Many public APIs, like the GitHub API, or even data from sources like the New York Times, provide data in JSON. The JSON method of the request response object automatically parses the JSON into Python dictionaries and lists. This is much cleaner than trying to parse text yourself. Regardless of whether you're scraping HTML or fetching JSON from an API, the goal is to get the raw data into a usable format for analysis. The pandas library is the go-to tool for structuring this data, usually into a data frame. The JSON method of the request response object automatically parses the JSON into Python dictionaries and lists. This is much cleaner than trying to parse text yourself. Pandas data frames are perfect for tabular data. For time series, setting the timestamp column as the index is crucial for using Pandas time series functionalities. Collecting data once is useful, but web data is often dynamic and constantly updated. To keep our analysis current and build an autonomous system, we need to automate the data collection process. Automating this involves writing a script that runs your scraping/fetching code periodically. This means putting your collection logic into a Python script that can be executed on a schedule. This script does two things. It defines functions for fetching and saving data, and then runs these functions when the script is executed, if _name == main_. This makes it runnable from the command line. To make it autonomous, you would then schedule this script to run at regular intervals using tools like cron on Linux, Task Scheduler on Windows, or cloud-based scheduling services. This is the core of the automated data collection. Saving the data persistently is crucial. Appending to a CSV file is simple for small data, but for larger scale, you might use databases, SQL, or data lakes with formats like Parquet. Pandas integrates well with these options. This script now forms the first part of our autonomous system, the data ingestion pipeline. It runs on its own, gathering raw data for us to analyze. We've built the data collection engine. Now, as data accumulates over time, we have a time series, a sequence of data points indexed in time order. Analyzing this data allows us to understand past behavior and identify patterns. The first step is always visualization. Plotting the data lets us see trends, seasonality, and anomalies visually. This plot immediately shows us the raw data's behavior. We can see the overall trend increasing, maybe some cyclical patterns like seasonality, and potential outliers, anomalies. To make these patterns clearer, we use techniques like resampling and moving averages. Resampling, like aggregating hourly to daily or daily to weekly, helps us see patterns at different frequencies. Moving averages smooth out short-term noise, highlighting the underlying trend. These analysis steps help us gain a deep understanding of our data's history and current state. But often, we want to look forward. The real power of analyzing time series data, especially for autonomous systems, is the ability to predict future values or trends, forecasting. This allows our system to anticipate events and potentially make decisions based on those predictions. There are various models for time series forecasting, ranging from classical statistical methods to modern machine learning and deep learning approaches. Classical models: ARIMA, autoregressive, integrated moving average, is a widely used method. It models the relationship between an observation and a number of lagged observations, the error term, and lagged forecast errors. ARIMA models often assume stationarity, that the statistical properties of the series don't change over time, which sometimes requires data transformations. Libraries like stats models in Python or the forecast package in R provide ARIMA implementations. Facebook Profit, mentioned as a good option, especially for daily or weekly data with strong seasonality. Profit is designed to handle common features of business time series, like trends, seasonality, yearly, weekly, daily, and holidays automatically. It's often easier to use than traditional methods like ARIMA, which require manual parameter tuning. Profit is available as both a Python and an R package. Profit is relatively straightforward. Prepare your data with DS and Y columns, fit the model, create a future data frame, and predict. It automatically gives you prediction intervals. For complex patterns or very long sequences, recurrent neural networks, RNNs, specifically LSTMs, long short-term memory, and GRUs, gated recurrent units, are powerful options. LSTMs are designed to remember information over long sequences, making them suitable for time series where current values might depend on data points far in the past. Libraries like Keras, TensorFlow, or PyTorch are used to build and train these models. Deep learning models, especially RNNs like LSTMs, require significant data preprocessing to structure the time series into input/output sequences, and training can be computationally expensive. However, they can capture complex, nonlinear patterns that traditional models might miss. Google Trends data is a great example of a time series that can be analyzed and forecasted. We can use libraries like PyTrends in Python or CrunchTrends in R to fetch this data. This gives us a pandas data frame indexed by time, ready for the same analysis and forecasting steps we've discussed. You could then feed this data into a Prophet or LSTM model to predict future search interest. We now have the pieces: automated data collection, time series analysis techniques, and forecasting models. The final step is to connect them into a robust autonomous pipeline. The simplest autonomous pipeline could work like this. 1. A scheduler triggers a data collection script, collect_data_script.py, at a set interval, for example, daily, hourly. So, the collection script fetches the latest data and appends it to your persistent storage, CSV file, database table, etc. 3. Immediately after, or triggered by the data update, a separate script, analyze_and_forecast_script.py, runs. 4. This analysis script loads the updated dataset from storage. 5. It performs the necessary time series, analysis, visualizations, smoothing, 6. It then runs the chosen forecasting model, profit, LSTM, etc., on the data to generate predictions for the next periods. 7. The analysis results and forecasts are saved, for example, to another database table, a file, or pushed to a visualization dashboard. This basic setup provides autonomy in data processing. However, a truly robust system needs more. Error handling. What happens if a website is down or changes format? Your script needs to log errors and potentially alert you. Monitoring. You need to monitor both the data quality, is the scraper still getting valid data? And the model performance, is the forecast accuracy declining? Retraining or adaptation. Time series patterns can change. Your forecasting model will need to be periodically re-evaluated and potentially retrained on the newest data. This can also be automated. For systems needing very rapid adaptation, concepts from online learning become relevant, where models update incrementally as new data arrives. Actionable output. How will the forecast be used? It could trigger an alert, update a dashboard, or feed into another system that makes automated decisions. This level of sophisticated automation, integrating data, models, and deployment, falls under the umbrella of MLers, Ops, machine learning operations. It requires careful planning and infrastructure. And there you have it, the blueprint for building your own autonomous system for collecting and analyzing live data and trends from the web. We've gone from the raw, messy reality of web data to structuring it, automating its collection, understanding its historical patterns through time series analysis, and predicting its future with forecasting models. The power of such a system is immense. It allows you or your organization to stay constantly updated on key metrics, spot trends early, react to anomalies, and make data-driven decisions automatically. Remember to start small, respect website terms of service, and build incrementally. This field is constantly evolving, with new techniques and tools emerging all the time. If you found this deep dive useful, please give it a thumbs up and subscribe for more on data science and machine learning. What autonomous system would you build first? Let me know in the comments below.